by heating with zinc dust. Zinc being a good reducing agent will reduce the benzene ring and take away the oxygen, you will end up with zinc oxide. So this is reduction of phenol. This is reduction. You are removing the oxygen. If you are putting more oxygen, that is oxidation of phenol. So this is basically oxidation of phenol. You can see if you use Na2Cr2O7, which is a famous oxidizing agent of a D block. So in this case, you can see there are two oxygen being connected. So it is formed benzoquinone. So these are redox reactions given by phenol. Okay. So this I hope is clear. Okay. Reduction by zinc dust, that is preparation of benzene also. So one more method of preparation of benzene now we are having, that is from phenol. You can treat phenol with zinc dust, you will end up with benzene and zinc oxide. Okay. And next is oxidation. Oxidation, if you treat phenol further with oxidizing agent like Na2Cr2O7, so you will have one more double bond O connected to the phenol at the para position, and that is basically benzoquinone. Okay. So do remember that this is also very important, both redox reactions given by phenols. So let's do this. And tell me what is going to be the answer. Yeah. Screen got unshared. Just a second. Yeah. Phenol is there, zinc dust. Then you react it with CH3Cl and AlCl3, and you heat the product Y with alkaline Phenol. So you can tell me quickly what is going to be the answer. So this is basically uh, benzene. Okay, zinc oxide is removed. This is Fieldcraft alkylation. Cl minus will be taken away by the AlCl3. CH3 plus will form, and that will react with benzene to give you toluene. If you heat it with KMnO4, this CH3 group will get oxidized to COOH. So this is basically benzoic acid. Got it? So this B is the right answer. Now this is acetylation reaction, very important. Just now we discussed acetylation for its use. Actually, we discussed its use, very important use of acetylation, and that is acetylation of the alcohol group or the phenol group of salicylic acid gives you aspirin. Acetylating agents, I told you, can be CH3COCl or they can be acetic acid. Both you can use. Okay. And you can acetylate normal alcohols or you can acetylate phenols. This AR means aromatic ring, like phenol. Okay, this is acetylation reaction. And there is one more important thing which you need to notice, where it asks many number of times, and that is that acetylation increases the molecular weight by 42. Okay, if you take this ROH and if you carry out it acetylation, HCl will be removed. Now a bigger group is joined and H plus is removed. So the change in molecular weight will be 42. This you need to remember. Very important. Okay. So there are other methods which involves removal of H plus from alcohol group or from phenol. One was acetylation, where the H plus was removed and the H plus was substituted by acetyl group. You have reaction with metals. Metals are electropositive, you know. So what they will do? They will lose electron. They will give electrons, and the electrons are being taken away by the H plus. Okay, because H plus is positive, so that surely the electron is going to come on H plus. H plus accept electron, and it get liberated as hydrogen. This is also a laboratory test for alcohols. Ethers will not give this test. For example, if you are given with C2H6O and you react it with Na and you don't see any hydrogen coming out, no H2 is liberated. It means this is an ether because it doesn't have any hydrogen. But if the hydrogen is being liberated, then surely that is an alcohol, or it could be phenol also, because they contain acidic hydrogen, right? So that I hope is clear. You can not only sodium, you can use potassium. You need a more electropositive element, aluminium. Okay, and sodium is the most common. Ethers do not get this test. Look here. So this reaction can be used to distinguish between alcohols and ethers. Okay. There are other reactions. So two reactions which we had seen were, in those reactions we were removing H plus of the alcohol. One was acetylation, another was reaction with sodium. Or any other active metal. There are other reactions where the O is completely removed. OH as a whole is completely removed. Removal of OH. Not only H, the complete OH is removed. The whole OH is removed. Okay. And that is dehydration, acid catalyzed dehydration of alcohol. Very famous reaction. This reaction also lead to the preparation of an alkene. Because if you have OH removed, you can't remove just one group, okay? You need to remove two adjacent groups so that what will happen to the valencies of both the carbon, okay? If you are removing two groups, the two bond will be freed and they will join among themselves. to give you a double bond. Got it? Double bond will form. So that will lead to the formation of an alkene, acid catalyzed hydration. So first of all, how the OH will be removed? So you need some acid. Okay. Look, you need some acid. H2SO4, some strong acid, and you need it in the concentrated form. Don't take dilute. Concentrated H2SO4 or concentrated H3PO. So what happens? This OH get protonated. Otherwise, the OH can't come out. If it get protonated, it becomes OH2 plus. This pulls the electron because OH2 is very polar, plus charge on oxygen. This pulls the electron of its bond and come out as water. You have a cation, and the cation, because you are heating, the H plus is removed from the adjacent atom, giving you a double bond. So simply you can think in this way, you are removing water. So this is basically dehydration. Because you are doing the dehydration, you need concentrated acid, don't take dilute acid. Okay. And you will end up with an alkene. The alkene which is going to form, if there are more options, in this case you do not have any option because it is a cyclic molecule, all sites are same. So more substituted alkene. More substituted or more branched. Alkene is going to form as a major product, main product. And this alkene is known as ZEC. This alkene is known as ZEC. Alkene. That can form and that will be the major product. Okay. This is the mechanism. There is one more thing which you need to notice is always check for the rearrangement. Rearrangement of carbocation can happen. Suppose if you have this carbocation, or let's suppose if you try to dehydrate this alcohol, this is neopentyl alcohol or 2,2-dimethyl propane 1-ol. So when you treat it with concentrated H2SO4, the OH get protonated, means H plus is attached, it comes out as water, you have a cation. The cation is primary, so it is highly unstable. Always, always, always check for the rearrangement of cation. Okay. In whole organic chemistry, wherever you have a cation being formed, check whether it can become more stable by shifting onto the adjacent position. If yes, then do the rearrangement, make it more stable, then proceed ahead. For example, if I'm preparing alkene, just now I said, so first you have to prepare the cation, check whether it can shift or not. If it is becoming stable, you can shift it to the adjacent position. You can further shift it to the next position if it is becoming more and more stable. There is no limit to number of rearrangements. You can do rearrangement 1 time, 2 time, 3 time by shifting the cation onto the adjacent position one by one. One by one, okay, that is very important. Don't do the rearrangement from first position to fifth position directly. Don't do that. Okay, and make the cation shift get more stable by shifting. Once you are sure that now it is the most stable cation. Form alkene by removing H plus from the adjacent carbon. Form a double bond. Make the alkene which has more number of branches around it. Carbon-carbon branches. Most substituted alkene is the most stable alkene, which will be formed as a major product. Got it? And this is known as set-set. Right? These are the things you should keep in mind while doing the dehydration of alcohol. If there are two alcohol, which one is going to dehydrate fastest or with maximum rate? The answer is the one which is going to make a more stable cation. So I should write dehydration can happen more easily if you have a more stable cation. Are you getting my point? This is RDS, rate determining step. It is the step which can control the rate of the reaction, right? So it can happen most easily if you have a secondary cation as compared to primary. The dehydration can happen more quickly on secondary. If you have a tertiary, then also it can happen more easily than on secondary, right? Here, so we will do that question, and this is for the ethanol. These temperatures are standard, so you should write them. But these temperatures are only for ethanol. Only for ethanol. If you take ethanol, if you heat it to 170 degree in the presence of concentrated H2SO4, the water will get eliminated. Elimination will require high temperature. You will get ethene. Water is removed at 170. If you take temperature of 140 degrees Celsius, 140 or 137, 170, then substitution will occur. You will have ethanol. So remember the options with the temperature also. At 140 you have ETO80, and at 110 you have H2SO4 being connected, so ethyl hydrogen sulfate being formed on ethanol. Got it? But these are the temperature for ethanol only, not for other alcohol. Suppose if you take a secondary alcohol, then definitely the reaction is going to be more quickly. You do not require that much high temperature. I hope you are getting my point. Okay. So let's do this. Very simple question. So what's going to be the answer to this one? Let's set it. Three dimethyl butane duol. Let us write the structure first. This is butane 2 all, means OH on the second position, and this is 3,3-dimethyl. Got it? If it is heated with concentrated H2SO4, I will make the OH protonated. I will get it protonated, remove it as water. You will have a cation being formed. This cation is 2-degree cation. It is connected on the carbon which has two branches. the methyl will get shifted onto the adjacent position, because that's how it will become 3D. One methyl I will pluck from its position and send it to the adjacent methyl shift or methanide shift. Now you have this cation at this carbon. The H can remove either from this, or from this. But I'm going to remove the H from the middle, from the internal carbon. I'm not going to remove the H from the outer carbon. Because I told you that the alkene which we are going to get is ZZ alkene or ZSAF, ZAITSAF. The spelling could be different, but the meaning is same. Okay. That most branch alkene is the major product. Most branch alkene, ZZ alkene, the alkene which has more number of carbon atoms around the double bonded carbon. That is going to be the major product, main, and this is going to be the minor product. Look, there are 4 carbon groups connected to the double bond. So major product, and this is actually the minor one. To have 2 carbon groups connected only to the doubly bonded carbon. Other side you are just hydrogen. So what is the major product which is obtained? 2,3-dimethyl butane. It's very simple. Got it? But you need to be careful while doing this. I hope this is clear to everybody. Let's move on to the next question. And one more question I will do. So suppose if I ask you to compare which alcohol can get dehydrated with concentrated H2SO4 most easily, what is the ease of dehydration? Are you getting my point? Rate of dehydration, ease of dehydration means I'm asking you where the alcohol is going to get dehydrated most easily and with most difficulty among these. So as I told you, the rate depends upon the stability of the carbocation. If you have a more stable carbocation, the alcohol can form most easily. The cation can form most easily and it will get dehydrated. But this OH will not get removed. Remember why? This is in resonance. And because of the resonance, this will acquire a double bond character. And if it acquire a double bond character, it will not come out easily. So D will not be dehydrated. Got it? Phenol can't be dehydrated. It can be reduced. One more thing, you cannot have triple bond on the ring. So phenol and the OH can't come out because it is in resonance. But these 3 alcohol can get dehydrated. Out of this, the C can form most stable cation because the cation comes between the 2 double bond after the removal of OH, and it is the most stable resonance stabilized cation. Then you have this cation which is also resonance stabilized, but only 1 double bond can help it to get stabilized. And then you have this normal cation. This is secondary but not undergoing resonance. So if I ask you rate of dehydration of these alcohols, so most easily for dehydration can happen for C, then for B, then you have it for A, and then for D. D will not undergo dehydration because it is phenol. the OH will not come. I hope this is clear to everybody, right? So now let's move to the next topic, and this is oxidation of alcohol. Alcohol get oxidized. Oxidized means removal of hydrogen. So you get hydrogen removed from the H and carbon. This is not removal of water. This is removal of hydrogen only. And if the hydrogen is removed, what you get? You get double bond. You get an aldehyde, you get a ketone, you get a carboxylic acid. Okay. This is known as oxidation of alcohol. Very important thing. First of all, primary alcohol. RCH2. Upon oxidation, a double bond is appear on the carbon oxygen. So if you take mild oxidizing agent, weak oxidizing agent, you just get aldehyde. But if you take a strong oxidizing agent, you will directly get up to acid, because this hydrogen connected to C double bond, that also get oxidized to OH. Oxygen will get connected to it. So I will like to summarize that the primary alcohol can be oxidized in two stages. If you do the oxidation in the mild manner, weak oxidizing agent, you will end up with aldehyde. And if you take strong oxidizing agent, you will end up with carboxylic acid for primary alcohols only. So two things you need to keep in mind. For secondary alcohols, there is only one option. Secondary alcohols have just HH and they will get removed, and you have C double bond. That's it. Got it? So ketone, and ketones are very difficult to oxidize further. Tertiary alcohol do not get oxidized, because if you have a tertiary alcohol, you have OH, but you do not have carbon. Carbon doesn't have the OH. Sorry. There is no H on the carbon. So how can you form a double bond? You need to remove the hydrogen from oxygen and from the carbon to get it oxidized. You do not have any hydrogen on the carbon. So alcohol, tertiary alcohol do not get oxidized. Secondary alcohol gives you ketone. Primary alcohol can give you aldehyde or carboxylic acid. If you use weak oxidizing agent, mild, you get aldehyde. If you use strong oxidizing agent, you will get carboxylic acids. Strong oxidizing agents are like KMnO4, K2Cr27, H+8. They are strong. Mild oxidizing agent are PCC, pyridinium chlorochromate, and copper and heat. Red hot tube of copper. This is delta. So I hope this is clear to everybody. Clear? So let's move ahead. Copper red hot tube is also very important. Mild oxidizing agent. Just now I told you copper heat. Copper delta is written. It can be written in this way also. That also instead of temperature. So copper 300 degrees Celsius. Okay. So you remove H and H. That is mild oxidizing agent. You end up with aldehyde for primary alcohol. This is mild. Means weak. If you take copper red hot tube, For secondary alcohol, HH will get removed. You get a ketone. If you take a tertiary alcohol, HH will cannot get removed from there is no H on the carbon. But OH and H get removed. But this is not oxidation, this is removal of water, dehydration of alkenes. So copper additive, you can end up with aldehyde for primary alcohol. You can end up with a ketone for secondary alcohol. You can end up with an alkene for tertiary alcohol. Tertiary alcohol undergo dehydration. I hope this is clear, right? Very simple. Okay. What are the mild oxidizing agent and weak oxidizing agent? I will write it once more for your ease. Mild and strong only affect primary alcohol. Mild means RCH. And mild is basically PCC. Pyridinium chlorochromate in CH2Cl2. What is pyridinium chlorochromate? This is pyridine with H plus is pyridinium and CrO4 CrO3 Cl minus. So chlorochromate is this one. This is a weak oxidizing agent. Okay. PDC pyridinium dichromate. Okay, that also is weak. But what are the strong oxidizing agents? Strong oxidizing agent, you will get directly acid for primary. Ketones will remain ketone. So KMNO4 H plus heat, K2Cr27 H plus heat. Okay, these are or CrO3 H2SO4 acetone. This is also strong oxidant. Jones image. This is also a strong oxidant. I hope this is clear to you. Right? Let's move on to preparation of alcohol from ether or reaction of ether. This is a very important reaction. Cleavage of ethers using HN. Ethers themselves are bases. Why they are bases? Because they have oxygen. Oxygen possesses lone pair. So ethers will not react with base because they themselves are base. But they can react with acids like HI. HI being strongest acid, so it can break the ethers apart. Suppose if nothing is given, then it is not a problem. Suppose if I ask you to react this ether with HI, so oxygen has lone pair. H plus will get connected to the oxygen and I minus will get connected to the R. So you can get ROH and R. Okay. So basically you have ROH and RI. This is, you end up with 1 mole of alcohol and 1 mole of alkali. If you take 2 moles HI, 2 moles of HI, again you will put one more HI. So with 2 moles, you will get Ri, this Ri, NH2. Got it? Clear? Ri, NH2. So normally this is not a problem if both are same. Then the reaction is very easy. Normally you need to think that if you have an unsymmetrical ether, you need to think where to put the I, where to put the OH. Okay. So it depends upon the mechanism. For example, this is unsymmetrical ether. You have two different groups. One is methyl, another is ethyl. Okay. And how they are going to interact, how they are going to react with ether, HI. Should I put I on the methyl or should I put I on the ethyl? That's what my question is. That's what the problem is. So what I need to do over here is, first I need to put the H plus. That's the first thing I need to do. That's the first thing which I need to do is put H plus. Now think, any of the alkyl group on the either side of this O, can they form a cation, stable cation? Yes or no? Cation will be stable if they are tertiary, if they have a resonance stabilized cation, like benzylic cation. This doesn't have any double bond. This group doesn't have any double bond, doesn't have any benzene. So they are not going to break and form cation. So if they are not going to form a cation on their own, now what to do? Now I minus will come in and attack on the carbon and will push out the oxygen. The oxygen is not going to break on its own. It will be pushed away by the R minus. So this is SN2 cleavage, where you do not have any stable cation, you have SN2 cleavage of ethers. I minus will join itself to smaller alkyls. So you have CH3I and ETH. Got it? Suppose if you have, so this is very important, right? And suppose if you have, and if you take 2 mole, this will also become ion. But that 2 mole is very easy because both you can make as iodides. But with 1 mole, you need to think that should I put I on methyl or should I put I on ethyl? Think in a very systematic manner. Okay. So I minus, if it is SN2, I minus is going to come on the smaller alkyl. If it is SN1, means cation, if anyone can form a stable cation, then I minus is going to come on the larger alkyl group which can form a stable cation. I hope this is clear, right? So let's do this problem. Cleavage of ethers using HI. So here you can see that this mechanism is going to be SN1. This mechanism, you can see it happening. Okay. because it is a more stable cation which can form, right? Very simple question. Cation can form easily on this because it is resonance stabilized. If it is resonance stabilized, it will break apart and I minus will come on this. So you are going to have CH2 ion and you are going to have phenol, more than one correct option as the product. Got it? What about this one? Cleavage of ethers. This can break apart easily, but this will never make, never break the bond in which the oxygen is directly linked to benzene. If it is directly linked to benzene, don't break apart that oxygen or that bond unless you are going to break it in this manner, because that is resonance stable and that has double bond correct. So what are we going to get over here? This I am going to leave as it is OH. So this one and this one could be the answer. Now I am going to break this bond. So O is going to come with methyl. This is incorrect. I can come here. This is correct. Got it? So D is the right answer. Here also I'm not going to break this bond. This is partial double bond character because of resonance of just we had seen it in the phenol also. This is CH3. So I'm going to use H and I. CH3I and OH. Here I'm going to break it. This is not directly, oxygen is not directly linked to benzene. So H and I. Understood? So here you are going to put the CN and I and OH. This is going to be the answer. Right? I hope this is clear. Okay, next question. If you have this, so this can come out very easily because this cation is going to be stabilized by resonance and the fastest reaction. If the benzene is having electron donating group at the para position with oxy group, it can form most easily. Okay. Right? So benzene having OCSA group can facilitate the formation of cation. Next question, organic compound C9H10 when treated with HI can goes cleavage means it is an ether. Give compound B and C, B gives yellow precipitate with AgNO3 means it will, yellow precipitate with AgNO3 means AgI will form. So B is having I, okay, because it can give yellow precipitate with AgNO3. C is tautomerism of D and gives positive hydrophone test. So let's check it. What could be the answer? So if you treat them with HI, let's say this one. This may be the answer, may not be the answer. So if you break it with HI, This cation can form easily because it is resonance stabilized. So CH2I, and this one OH, but this will tautomerize. It is going to form CH3 C double bond because that is more stable than double bonds. It gives positive hydrophone test. Yes, that is true. So this is the answer. Got it? This we already did this question. This also we did. Right? Aspirin is the acetylated product of orthohydroxybenzoic acid. Right? So I hope everybody understood this. Let's move on to the next chapter of aldehyde and ketones. So we will move to the preparation of aldehyde ketones. Okay. So aldehyde ketones. Let's. So these are some common example of aldehyde ketone from your NCERT book. Very important to know them, their common name as well as their IUPAC names. Okay, the IUPAC name of cinnamaldehyde is got it. Similarly, you can see what is this propane 1, 2, 3 tricarbonaldehyde. Acetyl oxide is just one. And 3 in 2O. And 3 in 2O. And you have a methyl on the fourth position. Got it? So these are some common uh, aldehydes and ketones from your NCERT. Vanillin, salicylaldehyde, 2-hydroxybenzene carbonaldehyde. Got it? So how you are going to prepare them? That's the question. Okay. So from alkenes you have a double bond. If you cut the double bond and put oxygen on both the sides, you have either aldehyde or ketone being formed in the reaction, and that can be done by ozonolysis by treating these alkenes with ozone O3. This ozone bind itself to the double bond and it form ozonide. This ozonide is unstable. It breaks into fragments, and these two fragments can be your aldehydes and ketones. But there is one very, very important thing you need to know about the ozonolysis, right? And that is whether you are doing the oxidative ozonolysis or reductive ozonolysis. If you are doing the reductive ozonolysis, you will have zinc or dimethyl sulfide Me2S written along with the ozone. Ozone followed by zinc. Ozone followed by Me2S. And those are actually the reductive ozonolysis. So in reductive ozonolysis, you are going to break the double bond, put O and O, that's it, complete, right? But in oxidative ozonolysis, look here, you have taken an oxidizing agent, H2O2. Oxidizing agent you taken. So oxidizing agent will oxidize. Whom it will oxidize? If you have an aldehyde being formed, you can check the alkene. So this will form a ketone because you have two alkyl groups. This will form aldehyde. You have one hydrogen and one carbon. Got it? And what happens is, so if you took oxidizing agent, it will oxidize the aldehyde to carboxylic acid. So only the part which is having the hydrogen will change to acid if you took H2O. I hope this is clear. So you can get acid also, you can get aldehyde also. But if it is a ketone, it is going to remain ketone whether you take oxidative or reductive ozonolysis. This is reductive ozonolysis, zinc is there, and you will end up with both as aldehydes. Cut it, put oxygen, that's it. If this is reductive, you are going to end up with aldehyde having 3 carbon atom, propanol. Okay. Now let's find the method to get aldehyde and ketone from alkynes. So from alkenes, you cut the double bond and you take zinc, right? And how you get the aldehyde and ketone from alkynes? That is by addition of water. Acid catalyzed hydration of alkynes. In alkynes, you add water. And you get enol form. This enol will undergo tautomerization where the double bond will get shifted between the double bond O and the S gets shifted to the carbon. You get a ketone or an aldehyde, depending upon the groups attached. So you add water to triple bond and you get aldehyde or a ketone. This addition of water can be carried out by using dilute H2SO4, just what we were doing in for the preparation of alcohols also. But here, because there was a triple bond, you are not going to get an alcohol, you are going to get an aldehyde or a ketone. And this addition, Hg2 plus act as a catalyst. So you take HgSO4, H2SO4, or sometimes it is just written Hg2 plus H2. Sometimes it is written HgSO4 aqueous. Sometimes it is written H2SO4, HgSO4. Got it? So that is Markovnikov addition of water, where the H is going to join itself to the terminal carbon, and the OH is going to come in the middle, and then you have tautomerization, and then you end up with a ketone. Got it? But there is a way by which you can put the water outside the OH group on the outer carbon, and that is by hydroboration. Hydroboration actually was used to do the anti-Markovnikov addition of water. And if you remember, anti-Markovnikov addition of water on alkenes, that was by hydroboration and followed by oxidation. So here also boron is a bigger atom. Look. So this H and this B. The boron is going to join itself to the outer carbon because boron is a bigger atom and it has alkyl groups. And with H2O2 and NaOH, this boron is going to get oxidized to OH. And you have tautomerization, so you will end up with an aldehyde on terminal alkynes. So these are the two ways. Either you can use HgSO4 dilute H2SO4, or you can use boron BH3 or B2H6 THF and followed by oxidation using NaOH H2O2. So let's look at for what we get with ethyne. Ethyne, you get ethanol, and propyne with HgSO4. The O is going to come in the middle. You are going to get an acetone, propanone or acetone. Okay. Here, so Markovnikov addition and anti-Markovnikov addition. Let me give you one question. If you have a pent-2 ion, how you are going to get 2 pentanol? And pentanol. So very simple. Triple bond is there. If you add water, you will end up with aldehyde ketone. If you want to add oxygen outside, use BH3, BHF, followed by NaOH, H2O2. If you want to put the oxygen internal on the internal carbon atom, HgSO4, dilute H2SO4. Okay. So this addition can be controlled, just like addition of HBr. Markovnikov addition, in which the Br was coming in the middle By direct HBr, the oxygen is coming in the middle with dilute H2SO4 and HGS. And in the presence of peroxide, in the presence of BH3, the oxygen is going to come outside. Getting my point? So that is anti-Markovnikov addition of water, but you don't get alcohol because this is an alkyne, you get an aldehyde or a ketone. Next step for the preparation of aldehyde and ketone is by oxidation of alcohol. So I told you just now also, because this is a common topic. In alcohol, it is the reaction of alcohols, oxidation of alcohols. For aldehyde and ketones, it is the preparation of aldehyde and ketones. So as I told you, that primary alcohol can be oxidized in two stages. If you use mild oxidizing agent, you will end up with an aldehyde. If you use strong oxidizing agent, you will get to acid. Only for the primary, you have two options. For secondary, there is no option. You will get ketone always. Tertiary alcohol, no oxidation. Only with copper, you will get an alkane. That is not oxidation, basically. So that's what we have seen. Okay. So H2CrO4 heat, just get oxidized. Ketone. This is secondary alcohol, you get a ketone. Secondary alcohol, you get a ketone. Primary alcohol, with PCCCH2Cl2, you will get an aldehyde. If you take KMnO4H plus heat, K2Cr27H plus heat, they are strong oxidizing agent, you will end up with a carboxylic acid. Okay. So that will be the preparation of carboxylic acid, right? Next is preparation of aldehyde and ketones from nitrite. So how can you prepare aldehyde and ketone from nitrite? So if I want to get an aldehyde, this is your RC. And if you want to get an aldehyde, look what is being done. First of all, you need to attach one hydrogen and replace this nitrogen by oxygen. So you need to do the partial reduction, not the complete reduction. And the partial reduction can be carried out using Stephen's reduction, SnCl2HCl followed by H plus H2O, steam and boiling. So with SnCl2HCl, this is SnCl2 is a good reducing agent. HCl, you are going to get CH double bond NH. And water, it will get hydrolyzed to CH2. Got it? This is partial reduction. Stephen's Sn and HCl, SnCl2 and HCl, Stephen's reduction give aldehydes. Okay. Or there is one more thing which you can do is you need one H. So don't use LiLH4. LiLH4 is having 4 hydrogens. So use just one H. Diisobutyl aluminum nitrate. This is known as divalH. This is the abbreviated name. Diisobutyl aluminum nitrate. This is the formula with one H on aluminum and 2 isobutyl. That is going to reduce this and followed by hydrolysis to aldehyde.